Ever played with a laser pointer, chasing that little red dot around? Or maybe you've watched a cashier use a barcode scanner at the grocery store checkout. Well, believe it or not, that's a laser in action. Lasers are more common than you might think, and they're used in a huge variety of applications. But what exactly a laser? The word laser is actually an acronym. It stands for Light Amplification by Stimulated Emission of Radiation. It sounds complicated, but the basic idea is pretty cool. To understand lasers, it helps to compare them to regular light. Regular light, like from a light bulb, is like a messy crowd with light waves going in all directions and different colors mixed together. Laser light, on the other hand, is a perfectly synchronized marching band. All the light waves are working together in perfect harmony. That means all the light waves are the same color, lined up neatly, and moving in the same direction. It's like the ultimate in-light organization. This incredible organization is what makes laser beams so super focused and powerful. Unlike a regular flashlight, which scatters light all over the place, a laser beam stays tightly focused over long distances. So what's the secret to this amazing light control? Well, laser light has 3 key properties. First, it's monochromatic, meaning it's just one color or wavelength. Second, it's coherent, which means all the waves are perfectly in sync with each other. And third, it's collimated, meaning the beam is narrow and straight, with very little divergence. Because of these properties, lasers can concentrate an incredible amount of energy into a tiny spot. Think of it like this. It's the difference between a gentle spray from a garden hose versus a high-pressure water jet that can cut through steel. In essence, lasers turn gentle, ordinary light into a precise and incredibly powerful tool, simply by organizing the light waves in a very specific way. And that's why, from scanning groceries at stores to performing delicate surgeries in hospitals, lasers are everywhere, constantly transforming technology and pushing the boundaries of science. So, next time you see a laser dot, whether it's from a pointer or a high-tech instrument, remember, it's not just a simple beam of light, it's a marching band of light, perfectly synchronized and powered by some pretty amazing science. Let's zoom in on a superstar, the YAG laser. That stands for neodymium-doped yttrium aluminum garnet, a crystal with a dash of neodymium. This solid-state laser is a workhorse invented in the 1960s and still going strong. It produces invisible infrared light at 1064 nanometers, a sweet spot for everything from metal cutting to eye surgery. The YAG is like a multi-tool. It can run as a steady beam or in powerful pulses, making it incredibly versatile. Its adaptability puts it in factories, hospitals, and labs worldwide. The neodymium is the magic ingredient, and the YAG crystal holds it all together. It's a classic example of how combining materials creates extraordinary technology. YAG lasers show material science at its best. Time to build an YAG laser. The heart is the gain medium, a carefully grown, pure YAG crystal rod. This rod is polished to perfection, with flat parallel ends to keep light from scattering. Doping is key. Scientists add about 1% neodymium atoms to the YAG crystal, replacing some yttrium atoms. These neodymium atoms absorb energy and release it as laser light, while the YAG crystal holds them in place. The rod's size and flawless finish are crucial for a strong, clean laser beam. Even a tiny imperfection can ruin performance, so manufacturing is ultra-precise. This isn't just a crystal. It's a high-tech component engineered for laser action. Without a perfect rod, you can't build a quality laser. It's the foundation of the whole system. The heart of our laser system is the laser rod. This specially crafted rod, often made of materials like neodymium-doped yttrium aluminum garnet, or YAG, needs an external source of energy to kickstart the lasing process. Think of it as the fuel that powers our laser engine. That energy is delivered by a powerful flash lamp. It's similar to the flash you'd find in a camera, but on a vastly larger scale, emitting a burst of intense light. These lamps are designed to provide the precise amount of energy needed to excite the atoms within the laser rod. To ensure maximum efficiency, the lamp and rod sit within a reflective chamber. This chamber is carefully designed to capture as much of the flash lamp's light as possible. The reflective chamber plays a crucial role in focusing that intense light directly onto the laser rod, ensuring that the energy is delivered where it's needed most. This precise focusing is key to initiating the laser effect. Often the chamber boasts an elliptical shape. This clever design ensures that almost all the light emitted by the lamp is efficiently directed towards the rod, minimizing wasted energy and maximizing the potential for laser amplification. This careful arrangement is all about maximizing efficiency, ensuring that as much of the input energy as possible is converted into laser light. Every detail is optimized to get the most power out of the system. Next, we add 2 mirrors, strategically positioned at each end of the rod. These mirrors are essential for creating the optical cavity where the magic of laser amplification happens. One of these mirrors is fully reflective, acting as a perfect barrier to the light. It bounces all the photons back into the rod, ensuring they continue to stimulate more light emission. The other mirror is partially reflective, also known as the output coupler. It allows a controlled portion of the light to escape, forming the laser beam that we ultimately use. Together, these mirrors create a resonant cavity that traps the light, forcing it to travel back and forth through the laser rod. This constant bouncing amplifies the light intensity with each pass, as the photons stimulate more and more atoms in the rod to release their own photons in a chain reaction. The partially reflective mirror, or output coupler, allows a small, carefully controlled amount of this amplified light to escape the cavity, emerging as the powerful and focused laser beam we observe. This entire setup, the laser rod, the flash lamp, the reflective chamber, and the precisely aligned mirrors, all work in perfect harmony to form the complete laser assembly. First, the flash lamp energizes, or pumps, the laser rod, injecting energy into the atoms within the rod's material. Then, the mirrors trap and amplify the light, creating a cascade of photons that builds in intensity within the optical cavity. Finally, the output coupler releases a portion of this amplified light, emitting it as a coherent and highly focused laser beam. And that's how we harness the power of physics to turn raw energy into a highly focused and incredibly useful laser beam. A testament to human ingenuity and our understanding of light. Let's power up! Pumping is the first step, feeding energy into the YAG rod using a flash lamp. The lamp's bright flash floods the rod with photons, which neodymium atoms eagerly absorb. When a neodymium atom absorbs a photon, its electron jumps to a higher energy level, an excited state. Think of it like kids on a trampoline. The flash lamp gives them a boost and they jump up, full of energy. The goal is to get as many neodymium atoms as possible into this excited state. This all happens in a split second, charging up millions of atoms. The YAG crystal's job is to hold the neodymium atoms steady. Pumping energizes the atoms, setting the stage for laser action. This is the laser's charging up phase. Now, the key to laser action: population inversion. Normally, most atoms are in their low-energy ground state. Pumping flips this, putting more neodymium atoms in an excited, metastable state. This metastable state is like a waiting room where atoms can hang out longer than usual. With more atoms excited than at rest, the system is primed for a burst of energy. It's like a theater with more people in the balcony than on the ground floor. An unnatural, unstable setup. Achieving population inversion is essential. Without it, you just have a glowing crystal, not a laser. The pumping must be strong and fast to keep atoms excited. Now the rod is loaded with stored energy, ready for the next step. This stored energy is the fuel for the laser beam. With population inversion achieved, it's time for the magic stimulated emission. An excited neodymium atom drops to its ground state, releasing a photon spontaneous emission. If this photon passes another excited atom, it triggers that atom to release an identical photon, same color, phase, and direction. This chain reaction multiplies photons rapidly, creating a powerful, organized beam. The mirrors bounce this avalanche of photons back and forth, amplifying the light. Finally, the beam escapes through the partially reflective mirror as a focused laser. For pulsed lasers, it's a single burst. For continuous lasers, the process keeps going. This elegant process turns random energy into the most organized light possible. That's the heart of laser action. YAG lasers are just one type in a diverse laser family, each with unique properties and applications. Understanding the different types of lasers available is crucial for selecting the right tool for a specific task. From solid-state lasers to gas lasers and beyond, the world of laser technology is vast and ever-evolving. The Ruby laser, the first ever, holds a special place in the history of laser technology. Its invention marked a turning point, paving the way for countless advancements in the field. It uses a ruby crystal and produces visible red light, a characteristic that made it easily recognizable and useful for early experiments and demonstrations. The vibrant red beam was a symbol of this groundbreaking invention, but it's less efficient and only works in pulses, limiting its applications compared to more modern laser designs. The pulsed nature of the ruby laser meant it couldn't sustain a continuous beam, which was a significant drawback. CO2 lasers, on the other hand, use gas, not crystals, as their active medium. This difference in design leads to vastly different performance characteristics and emit far infrared light, a wavelength invisible to the human eye, but incredibly useful for various industrial applications. This invisible beam packs a powerful punch, making them perfect for cutting wood, where the infrared light is readily absorbed, leading to efficient and clean cuts. The CO2 laser is a workhorse in woodworking industries. Plastic, another material that readily absorbs the CO2 laser's infrared light, making it ideal for cutting and engraving. And fabric, where precision and clean edges are essential, making CO2 lasers a popular choice in the textile industry. But not metals, as the infrared light is largely reflected, rendering CO2 lasers ineffective for metal processing. The beam simply bounces off the surface. YAG's 1064 nanometers wavelength is ideal for cutting and welding metals, because metals readily absorb energy at this wavelength, where CO2 lasers would just bounce off, highlighting the importance of wavelength selection for specific materials. Compared to ruby lasers, YAG is more efficient, converting a higher percentage of input energy into laser light. It can run continuously, providing a stable and consistent beam, and pulses faster, allowing for more precise control over the laser's output, making it a modern favorite in industrial, scientific, and medical applications. Its versatility and reliability have made it a staple in many fields. There are also dye lasers, which use liquid dyes as their active medium, offering a unique advantage, and tiny diode lasers, compact and energy efficient, finding widespread use in consumer electronics and telecommunications. Each laser has its specialty, excelling in certain applications due to its unique properties and characteristics. Choosing the right one is like picking the right tool for the job, ensuring optimal performance and desired results. You wouldn't use a CO2 laser for microsurgery, where precision and minimal tissue damage are paramount, or a diode laser to cut steel, as it lacks the power and appropriate wavelength for such a demanding task. YAG lasers strike a balance between power, precision, and versatility, making them a popular choice for a wide range of applications. They are powerful, precise, and versatile, capable of handling both delicate and demanding tasks with ease, especially for metals and medical uses, where their specific wavelength and power output are ideally suited. That's why they're so popular. Their combination of performance and adaptability makes them a valuable tool in many industries. The YAG laser is everywhere an industrial and medical superstar. It cuts, drills, and welds metals with pinpoint accuracy, shaping parts in your phone or car. It marks serial numbers and barcodes on products fast, clean, and permanent. In medicine, it performs delicate eye surgeries and minimally invasive procedures deep inside the body. It's used for hair removal and tattoo removal, and even in scientific research and the military for targeting and measuring distances. Artists use it to clean priceless artifacts without damage. Fun fact: green laser pointers often start as YAG lasers, with crystals converting infrared to bright green. The YAG laser is a powerful, versatile tool that's changed our world.